That's guys and girls.
Yes, we have
Well, guys,
Susan and Kate are here now.
guys in America is unisex, but ladies and gentlemen.
Now, gentleman is the wrong word.
Ladies and physicists.
Lady is okay.
Yeah, ladies fine.
Ladies and physicists.
I refuse to be a gentleman.
Ladies and gentlemen,
I
and
refuse
other
to have
ones.
called a gentleman.
So the second talk of the day, Paul Dellar from the Mathematical Institute at Oxford will talk about Lattice Boltzmann methods, which according to Bill is the ultimate way forward.
Well, thanks for the vote of confidence. So yes, I'm going to talk about Lattice Boltzmann approaches for simulating MHD and systems not too far removed from MHD. I'll start off with some material on Lattice Boltzmann hydrodynamics. I don't know how many of you have met any of this area before, so I'll try and explain how it works in Navier-Stokes before trying to make it more complicated. Talk about doing regular MHD, two aspects there, how you put the Lorentz force in and how you simulate the induction equation. And I'll talk about some extensions to Brzezinski MHD, and I thank Alex for giving me a push to work on this. Ohm's law of current dependent resistivity, and finally show that I can actually get the full set of Maxwell's equations out of my scheme. So here on one slide is a 2D Lattice Boltzmann algorithm, which will simulate nearly incompressible Navier-Stokes. So I have a lattice. You'll get quite sick of this picture with 9 velocities which go along the axes and diagonals of a square grid. So you think of having a square grid like doing a finite difference code, and particles hop around on this grid going either along the axes or along the diagonals. They're numbered 0 to 1 in the center that goes nowhere, 1, 2, 3, 4, 5, 6, 7, 8. Each of those speeds has a weight associated with it, and they go into some equilibrium distribution functions here, which are known functions of density and velocity, and the density and the velocity are got from moments of some distribution functions which I call f. So I got 9, oops, these should have bars on them. So I got 9 functions, f0 up to f8 per grid point, and they evolve in space and time through this formula. So I do some collisions of f towards f0, add that onto the f value, and then move it to a new grid point at a new time step. So that's my numerical scheme.
Could you dwell on, a lot of people here probably don't know that staying on grid points, how important that is. I mean, it's the lattice part isn't familiar to us as a community.
Okay, so
Well, maybe he was going to show us, right?
I don't know, this might be the only introduction that he's going to go on.
okay, well, I was going to come back, but this is just sort of a
Erasers. Is there an eraser there?
yeah.
Ultimately, you have to show that this is approximating the Navier-Stokes equation.
Well, I'll certainly do that in detail.
Okay.
It's just the algorithm.
Are these? I'm puzzled. These weight factors, those are fixed, or they?
They're fixed. So have I got a? So I've got a square grid, just as though I was doing a finite difference scheme, and at each point in the grid, I've got a set of 9 particles, and they have speeds attached to them, which I'll just draw with small arrows. So there are my 8 moving particles sitting at this grid point, and and the time step is related to the particle speed, such that the particle that's moving up this way will hop from this point to this point in one time step. So the particle that was here moves to there in one time step, and the particle that's got this velocity moves from here to there. And then in the next time step it will go up there, and so on. And so that's the bit with the xi plus x plus xi delta t bit. The other bit is having a fake model of a collision operator which happens locally at each point on the grid. So the different distribution functions transfer amplitude to each other in a way that conserves the total mass at the point and the total momentum at the point, but otherwise brings the distribution function towards equilibrium. So as I'll explain later, it's a cartoon model of a real kinetic theory. But I like to show, this is more motivational, it might actually be useful for something. This is the Minion and Brown benchmark, which has been used in the incompressible Navier-Stokes CFD community as a way of seeing what happens with different numerical schemes when you try and solve a problem that you can't really resolve on the grid you're using. So their initial conditions are two anti-parallel shear layers which are perturbed with a little bit of a wiggle. So here are two fat shear layers, and there's slightly perturbed, so which way up is it? That was going up, that's going down slightly. So when you let it evolve, you get a Kelvin-Helmholtz instability, so you stretch out shear layers here and you roll up into two big fat vortices. When you start with fat shear layers and lowish Reynolds numbers. This is just a 2D Navier-Stokes problem. And then what Minion and Brown wrote about is if you crank the Reynolds number up to 10,000 and make the shear layers thinner, you see what you can get on a 128 squared grid, and you find that all the centered kinds of schemes, say spectral centered differences, they all blow up. And all the upwind schemes, like Godunov projection, they form spurious vortices. So I'm going to show some Lattice Boltzmann computations of the same benchmark. This is plain vanilla Lattice Boltzmann. I'll explain where BGK comes from in a moment. And if I crank the Reynolds number up to 30,000, then it blows up in the way that's characteristic of a central scheme. If I go to 256 squared, it becomes stable, but you form a spurious vortex, like an upwind scheme. And you finally go to 512 squared, you get a correct-looking solution. The shear layer does not cause an instability, and it doesn't cause a spurious vortex. But if I then do a modified form of Lattice Boltzmann, which I'll explain later, then even on 128 squared, you get qualitatively the correct solution. You've got straight shear layers, no instability, no spurious vortex. So as far as I know, the only numerical scheme that can do this problem with these Reynolds numbers on a 128 squared grid is Lattice Boltzmann. So it may be useful for something. It's not a totally insane way of doing CFD.
It's 128 squared in physical space times 8 in velocity.
Yes.
Times 9 in velocity
Yes.
space. So you could crank up the resolution of a
You,
finite volume code.
well, you could, but
At the cost of
at the storage cost if you had a sufficiently cheap algorithm that didn't need any internal storage.
You can think of the 8 velocity space points as equivalent to solving another 8 equations, right? So normally you would solve 5 equations or something. You included pressure.
Well, or you could do incompressible and spectral, you could just do vorticity and stream function.
Well, also once you do have those 8 points in velocity, you can crank up the spatial resolution even more, right? Presumably you start gaining more as you go into higher spatial resolution.
Higher Reynolds number.
Well, you can go to higher Reynolds number, but I don't see this trade-off between the. Well, I can see you might think it's fair to compare total number of degrees of freedom,
Right.
rather than spatial resolution.
Right.
But then, depending on how you write your code, you have one or more scratch arrays, so you ought to include those in the counting.
One or more what?
Scratch arrays. So you work out the Jacobian vorticity and stream function, and then you add on another bit to get the viscous term. So the thing about Lattice Boltzmann is that the only storage you need is just the storage for the current state. There's no extra working storage is needed.
We should go on. It's just factors of 2 to 4 in the number of degrees of spatial resolution.
So what's the motivation for doing it? So the motivation comes from thinking about if we do fluids 101, Newton's second law following a blob of fluid, then we can write down mass times acceleration is the force. But as soon as we stop thinking about following blobs of fluid but sit at a fixed point in space, we get a u dot grad u, something that's nonlinear, just because we have to map from a Lagrangian time derivative to a time derivative at a fixed point in space. So even if this force is linear, as it would be if we had an isothermal Newtonian fluid, so the pressure is linear in the density fluctuations and the viscous stress is linear in the velocity gradient, we get something that's non-linear because of that, the u dot grad u. Whereas if we go to a kinetic description, so instead of thinking about fluid density, fluid velocity, I've got lots of particles, each of which has a velocity vector attached to it. And then I've got a distribution function that lives in a bigger phase space, so it depends on both position, velocity, and time, instead of just depending on position and time. But the attraction is that the Boltzmann equation gives me linear advection. All the nonlinearity gets bundled into the collision term. But the price of that is going to a function of 7 independent variables rather than 4. And the Lattice Boltzmann world tries to fit in the middle, that we keep the linear advection from real kinetic theory, but we keep the number of degrees of freedom under control, so we're not expanding the state space enormously compared to doing a Navier-Stokes description. So that's the motivation, to try and keep the small number of variables from this description and the linear advection from the kinetic theory description and use that to build a numerical scheme. And the way to do that is to try and copy the essentials of real kinetic theory. So I'll just do a little summary of real kinetic theory. So I've got a distribution function which depends on position, velocity, and time. And I define hydrodynamic things from moments. So I integrate out dependence on particle velocity, and that gives me a density, a fluid momentum, and a fluid momentum flux. And then from my Boltzmann equation, I can take moments and I can get exact conservation laws for mass and momentum. No right-hand side because my collision operator conserves mass and momentum. But my momentum flux isn't conserved, so I can still work out an evolution equation, time derivative, divergence of next moment, and now I get a collision term which says the momentum flux relaxes to an equilibrium value on time scale, which I can calculate if I know more about the collision operator. And this is the exact, say, for real Boltzmann equation with Maxwell molecules or Fokker-Planck or various kinds of synthetic collision operators over here. So once I've got these moment equations, I get hydrodynamics out by looking for slowly varying solutions that evolve on a time, capital T, macroscopic timescale that's much longer than the collision time. So here's my set of moment equations, and I seek slowly varying solutions. I expand all the higher moments, the ones that are not conserved by collisions, as series in, I'm going to use tau to be lazy for the collision as the expansion parameter, and also do a multiple scales expansion of the time derivative, and then I substitute in collect terms at each order. For instance, the viscous stress I get from the leading order approximation to this equation. It's like that. So I've got an expression for pi1 in terms of div q0, which I can work out if I know q0, and I can work out the leading order time derivative of the leading order momentum flux using lower order equations, thanks to the multiple scales expansion. So if I get the same moment system, and I get the same pi0 and the same q0, I can't tell whether I started from the real Boltzmann equation or from a fake discrete one. Because by the time I've got down to the equations on this slide, I've forgotten the difference. So I can get to the same halfway point, and from then on, deriving hydrodynamics, it doesn't matter whether I got these equations from the real Boltzmann equation or from a discrete one. So what do we need from real kinetic theory? We need the fact that the distribution function tends towards an equilibrium under collisions, and we need to know some moments of the equilibrium. So the 0th one says that we get its integral is the density, next moment's velocity, momentum. Moment after that's the Euler momentum flux. I'm using theta for RT just to make life convenient to scale out gas constants or Boltzmann constant. And I need the third moment to be this expression. And all these things I can work out because I know what the real Maxwell-Boltzmann distribution is, and I can just do integrals to work out these moments. So if I can reproduce these moments and write moment equations from discrete kinetic theory, I get Navier-Stokes just as well as I get it out of real kinetic theory.
And this zero order heat flux, there's no collisionality dependence?
This is all in moments with respect to particle velocity, not peculiar velocity. So it's not. So the first correction would depend on the collisional terms, but the equilibrium one doesn't.
Where did Q0 come from in the previous slide?
So it appears because I need the evolution equation for the momentum flux. And I'm always doing moments with respect to particle velocity. So this is the whole momentum flux, not the pressure. And it contains a divergence of the third moment. And to,
okay, sorry, this is fine. Okay.
so I just need to work that out.
Yes. That contains fourth order.
This contains third order moments, and its evolution equation would then contain the divergence of the fourth.
Okay.
So it's the usual kind of lack of closure.
Yeah.
Closure that the evolution equation for each moment involves the next higher moment.
It's an energy flux, not a heat flux.
Yes. But if you formulate using peculiar velocity, it would be a heat flux. So I'm going to try and reproduce this in a discrete system. So how can I do it? Well, first of all, I can get rid of that Boltzmann's collision operator and replace it with BGK form. So I just let F relax towards an equilibrium with, to be simple, just one timescale tau, which I put in by hand. And as long as I calculate my F0 using a rho, u, and a theta calculated from F, I've still got conservation of mass, momentum, and energy, and F tending towards F0, so that's all I actually need to get Navier Stokes. But the difficulty is I now need to know what F0 is in order to supply a formula for it. If I'm doing real kinetic theory, this comes out of Boltzmann's collision operator. When I go to a BGK collision operator, I have to know what this is in order to put it in by hand, and this is often the hardest bit of constructing a Lattice Boltzmann algorithm, is working out what this ought to be. So having simplified the collision operator, now I'm going to chop down the velocity space. So psi is going to be no longer a continuous variable, but it's going to be forced to live in a finite set, such as this 9 I've shown before. And then instead of having f of x, I, and t, I have a set fi of x and t, where it's just convenient to move the velocity label down here. And my integral moments become sums, so my density is just the sum of the fi's, momentum, weighted sum of the fi's, or weighted sum of the particle momenta, similarly for momentum flux. So anything I could do starting from continuous kinetic theory, I can do the same as long as I write it using moments, because the moment system is the same. So that tells me how I can get a discrete scheme which gives me a PDE system, which is the same as I would get from doing Maxwell's equation of transfer in real kinetic theory. But I still need to turn that into something I can turn into particles hopping around on the grid, so I can program it on a computer. The way I like to think about that is, here's my discrete Boltzmann equation. It's still a PDE because it's only discrete in particle velocity. It's still continuous in time and continuous in space. But what I'm going to do with it is recognize this thing as being a derivative along a characteristic, and the characteristics coincide with those arrows I drew over there. So I can integrate along a characteristic for a time step. And this, being the integral of a derivative, exactly gives me function value at old point, old time step, function value at new point, new time step. So that's an exact integration of this derivative. Where I have to approximate is the integral of the collision term. And notice I've got this x plus I, s, t plus s. So s is labeling the position on the characteristic. So s equals 0 would start here, and then s equals delta t would bring me all the way up here. I'm trying to do the integral of the collision term along this line. And I'm going to try and do that by the trapezium rule, so I take half the value at one end of the characteristic, half the value at the other end, multiplied by the time step. And that gives me something that's a second order accurate approximation. The problem is that it's implicit, because this f at t plus delta t depends on omega at t plus delta t, which depends on f of t plus delta t, and also f0 at t plus t delta t, and f0 depends on the s through the rho and the u. So this is a nasty nonlinear coupled system that I would have to try and solve for the f at the new time steps. But there's a nice trick. If you take everything that depends on t plus delta t over onto the left-hand side, you can collapse up like this, and you just give this a name. You call it f bar, which is f plus half a time step worth of collisions, and then this exactly rearranges into an explicit formula for f bar at the new time step. So this is an exact rearrangement of this, but it's in the form of a fully explicit scheme which looks a bit like forward Euler, except where I started off with 1 over tau, I get 1 over tau plus delta t over 2. It comes from this change of variables. And then the clever bit is that I can reconstruct the density and the momentum just as easily from the f bars as from the f's, because I know that adding on this collision term doesn't change the density and it doesn't change the momentum. So I've been asked sometimes, well, why don't people use this to integrate general ODE systems? It's because you can't, in general, do this inversion to reconstruct the ODE system you want to solve for f in terms of f bars, but because of this particular structure, you can do so. So this is the formula which gets coded up. It tells you how to revolve the f bars from their old points at old times to new grid points at new times. But there is a problem with this. When I started off with a PDE, and if I look at the PDE, all these f's relax monotonically to equilibrium over some time scale tau. That's what this right-hand side does. But when I've discretized it, that's no longer true. So if I think about spatially uniform solutions, just to make life easier, I can rearrange it to show that f bar difference from equilibrium is multiplied by this factor in a time step, and when tau is small, this factor gets close to -1. So rather than approaching equilibrium monotonically, you overshoot and oscillate around. So here, for example, I'm comparing what you get with solving a discrete Boltzmann equation, where you have an initial transient over a timescale tau, and then some slowly varying solution. And the Lattice Boltzmann scheme is tracking that, but it's tracking it with superimposed high-frequency oscillations, because the tau is small compared to delta t. So you sort of think about, you don't expect you can solve an ODE system for time step much bigger than the time scale of the ODE you're trying to solve, but you can get away with it because you track the slowly varying solutions, and hydrodynamics is slowly varying solutions of a kinetic equation.
So it can be better for dissipated, you're kind of doing Crank-Nicholson on a strongly dissipated term, and it can be better to be backward Euler than try to be second order.
Well, if you do backward Euler, you find it's much too dissipative.
You can then try second order backward differentiation, or there are other variations.
But I don't know if you can show that they capture the slowly varying, because you don't actually care about this. You want to get the slowly varying solutions, and the Crank-Nicholson style discretization gives you that. And also what I'm showing here would be something that's not conserved, for instance, the momentum flux, but the momentum is evolving through lots of successive increments coming from the momentum flux at each time step. So these, when you start summing them up, the conserved variables look much better than this, because these oscillations almost exactly cancel out every time you do a pair of time steps. Here's a numerical example just of a simpler system of Berger's equation. I put in the Gaussian initial conditions, and then I let it steepen up and form a shock, which then starts decaying. This was a run on 1024 grid points with tau 0.01 in the so-called lattice units, where you take the time step and the grid spacing to be length 1. Interesting that the same or equivalent algorithm was run on a so-called type 2 NMR quantum computer, but with only 16 points. So one of the attractions of these algorithms is they are very simple to implement. So here's some MATLAB, which I used to reproduce that picture. This is a Lattice Boltzmann set up for Berger's equation. These are my two kinetic equations, and my conserved variable in Berger's is the sum of these two. So the algorithm is I work out my conserved variables. Here it's just a row from my distribution functions. Work out my equilibria, collide my distribution functions towards the equilibrium, and then the streaming just involves shifting particles around on the grid. So I can do Berger's equation in 7 lines of MATLAB and wrap it up in a loop. Now, one way to deal with those oscillations, and this will come up again later, is to notice that what I need to get hydrodynamics is just this system of equations, which only involves 6 distributions, so 6 degrees of freedom. I've got one density in 2D, 2 components of a vector, 3 components of a symmetric tensor, so that's 6 degrees of freedom. But on this lattice, I keep showing you I've got 9. So there are 3 have disappeared. So it's useful to define 2 new moments, one scalar, one vector, and this is just another set of weights, 1 in the middle, minus 2 along the axes, and 4 along the diagonals. So now I can do a complete reconstruction of the whole distribution function, involving not just density, momentum, and momentum flux, but also these n and the j. So if you like, this is doing a change of basis from my 9 f's to a set of 9 moments, and the advantage of having a basis is that I can go backwards and forwards. And for describing the collisions, it's much easier to do it in terms of the moments, and then reconstruct the distribution functions rather than trying to write down a collision operator directly for the distribution functions. So I'm going to extend a little bit and allow myself to have some matrix here. I have a matrix collision operator, but this matrix is designed so that the moment system I get decouples nicely. I've got my stress, momentum flux relaxing to equilibrium with some timescale tau, my j moment relaxing with a different timescale tau j, and my n with yet another moment. That's a timescale, so it's tau n. And these sort of decouple, but they couple that when I project this and this onto my basis, I get some j's appear in here, and some pi's and some u's appear in there. So I've got a coupled system of 9 PDEs, which gives me an equivalent description of the Boltzmann equation, and the attraction is this is set up to get hydrodynamics out, because hydrodynamics involves the moments, not the distribution functions. And now this is still a PDE system. I have to do the same integration along characteristics trick to make it discrete, and then I get the half delta t's appearing down there, and these things have got bars on to indicate that they're moments of the bar distribution functions. So what I would do is do my collisions in the moments, so I'm relaxing momentum flux, n and j towards their equilibrium values. Then I reconstruct the post-collisional distribution from these moments in terms of this formula. And the attraction here is if I choose, say, tau n and tau j to be a half delta t, that has the effect of setting the n and the j just to equilibrium after every time step. And that's much more stable than over-relaxing things that there's no need to over-relax because they don't appear in the Navier-Stokes equations.
What are n and j physically? They look like some kind of breathing mode, or?
So j is part of the Q, or the energy flux, that fits on this grid, and n would be one higher. So it's the surviving part of the fourth moment. I don't know if there's a good. It's something that you would need to get the heat conduction. So that's the end of Lattice Boltzmann hydrodynamics. Now to talk about MHD.
Maybe before you do that, so the viscous stress term in Navier-Stokes is second order in space derivatives.
The stress is only first order.
Stress.
Yes.
The divergence of the stress.
It's second order.
And that term is related to heating, viscous.
Yes. So what I presented is just an isothermal model.
So I mean, so you don't somehow reproduce the Laplacian essentially quite correctly in this.
Well, I do, because I get from way back here. So I work out what all this stuff is, and I get pi. So I know what Q0 is, and I can work out T0, pi 0, and then it's just a messy piece of algebra to get
somehow I mean, I haven't followed this field. In the very beginning, when people were writing down these models, it seems to me, I recall that you only got the stress right at very long wavelengths, or something like that.
Well, this is all only right at very long wavelengths because I'm doing a Chapman-Enskog kind of expansion.
Well, right, but I mean, if you take the Navier-Stokes equation as exact at all scales, including very short ones, you get all the scales right, including very short ones?
All the spatial scales, because the old relationship between the collision time or the mean free path and the grid spacing, which you used to have in a lattice gas, has been removed. So you can take the Tor much less than delta T, or you can make your mean free path much less than the grid spacing. So you can still be in a Navier-Stokes regime even down at the grid scale.
Okay. There were also things about symmetries that obviously you can't expect to reproduce continuous symmetries on this lattice.
Well, you reproduce an isotropic viscous stress, so you've hidden the anisotropy down at the Burnett and higher levels in the Chapman-Enskog expansion.
Mm-hmm.
So at the Navier-Stokes level, you do have isotropy. But there are various artifacts of the old lattice gas. For instance, if you don't have those diagonally propagating particles, you find the momentum along each row and each column is spuriously conserved.
Maybe that's what I'm thinking of. So the diagonals are important.
And they're necessary to break that spurious conservation law, and they're also necessary to give you an isotropic viscous stress. There were earlier artifacts of the lattice gas. You had to have a Fermi-Dirac, discretized Fermi-Dirac distribution or the Boltzmann distribution, so you got sort of quantum-like effects, which meant that the pressure ended up being non-Galilean invariant, but those have gone in the sort of 1990s version.
When was this implicit treatment of the collision operator introduced?
This formulation is from 98, but it's mathematically equivalent to what everyone was doing before then. So what you can do is you can start out with what looks like a forward Euler discretization, and you start expanding out the discrete scheme in Taylor series, and you find that you can remove a truncation error and collect it into the viscous stress, and that tells you the way you should have had a discrete collision time, call it Tor discrete. You actually get Tor discrete minus delta T over 2. So it's all consistent. It's just you can start either from the PDE end and try and discretize, or from the discrete end and then try and work backwards to a PDE. And I find it easier to start with the PDE I want to solve and then do this, because sometimes you would have to be very ingenious to spot the right discrete system. Particularly if you're including body forces, because then that F to F bar transformation changes the velocity, and you have to account for that.
Do you have any? Can you describe the state of the art in using this to do problems? Is this widely used these days, or is it a niche market? What's going on in hydro?
In hydro, I've got slides, but it'll probably take me too long to find it. It used to have about 60% of the car industry use Lattice Boltzmann to do their engineering CFD. There's a company called Exa Corporation that has a software package called PowerFlow, and this had the majority of the market in the car industry.
Sounds like him.
Yes, but they're not so happy at the moment because the car industry isn't buying software packages due to the general economic climate.
Is it always going to? I mean, with the car industry, at some point you probably got a software package that will do you forever, right?
Well, upgrades.
They sell upgrades. So people like it because you can do, say, resolved flow through the front grille and round the engine and out through the wheel vents and all these kinds of complicated internal flows. But yeah, you're still using a turbulence model bolted onto this, and there is always room for improving the turbulence model. For more sort of academic pursuits, one of my colleagues in the US is brave enough to go up against Spectral for doing 3D periodic boxes turbulence simulations. And he's seeing very, very nice agreement, surprisingly, when you compare what might be second order accurate against spectral. If you you look at, say, time instantaneous structure functions, they agree very nicely. So I'll show some big MHD computations later on.
Even for very high order structure functions, you're not going to get them wrong somehow by this method?
It seems not, whereas if I understand if you do a finite difference or finite volume discretization, the people who advocate these methods are not very confident about comparing instantaneous structure functions rather than time averages against spectral.
Well, they should be time average, I suppose. But I mean, in principle, if I were to compute a 10th order structure function of the velocity, this method and time average, if this method would give you the correct.
I don't know if anyone's done the 10th order, but all the ones
Well,
that...
just in theory.
Well, yes, it should do.
But 10th order, you don't even know what's correct because you can't even do it.
He's just asking,
No,
does
just- Can't
even do it
does the lack of
experimentally.
symmetry underneath run out of gas when you're trying to use it to compute something?
No, you can get a Navier-Stokes solution as accurately as you wish, depending on that. You just have to throw enough computer power at it. And what people are finding is that you don't need absurd amounts of computer power to get that. So it's like the sort of the molecular dynamics world where you find that 10 molecules across and it starts looking like a fluid. And it's easy to take the collision time, or the mean free path down below a 10th of a grid point. So what I was showing you before, you can run it at 100th of a grid point. So you're well into the hydrodynamic regime, even down at the grid scale.
There was no need to choose these velocities in to be awarded the thermal velocity. What if I made them a 10th of the thermal velocity?
Well, so when I'm just doing incompressible, then I don't, as long as the thermal velocity is big compared to the fluid velocity, I don't care. Well, what you tend is you rescale the fluid velocity. So you have so you're doing order Mach number perturbations around an isotropic sort of Maxwell-Boltzmann equivalent. The whole story for doing honest thermal flows at order 1 Mach number is rather less well developed. All the obvious things which would give you compressible Navier-Stokes Fourier when you do the Chapman-Scott expansion, they're not very stable.
Okay, we should go on.
No, we should.
Sorry. Yes, I'm sorry. But that makes me worry suddenly. You've got a finite velocity, anything you move at in the grid. Particles can only move at a certain velocity on the grid.
Yes.
That's not a velocity relative to the flow velocity.
No, it's absolutely so it's not like doing grad 13 moment where you expand around in the frame of the local fluid velocity. This is all in some absolute frame.
Yeah, but doesn't this mean that you can't have a flow that's very much bigger than Mach 1 or bigger than Mach 1? Because none of your particles go faster.
So what you can do, so if you were doing real kinetic theory, you get stuck there, but in discrete kinetic theory, you can decouple the thermal speed from the particle speed just by changing the equilibrium. So I can do the limit where thermal speed is less than the fluid speed, and both are much less than the particle speed. So in principle, I can converge to Navier-Stokes Fourier for whatever Mach number you want. However, it's actually...
But the particle speed is the speed that they jump one of these
Mhm.
lattice points.
Yeah.
You know, delta x over delta t.
Yeah, but
That
because-
always has to be faster than anything. Right?
It does. But the thing is, in real
That's
kinetic...
not your thermal speed.
In real kinetic theory, because you've got that, you're stuck with a Maxwell-Boltzmann distribution, so there's always a relation between the particle speed and the thermal speed. Here I can write down my Fi0 to be anything I want. So I can write something down where the thermal speed and the sound speed are both much smaller than the particle speed.
Okay.
So in principle I can converge to Navier-Stokes Fourier for any Mach number.
Sorry, I didn't. So your Fi0 is not then the equilibrium solution.
Yes, but the equilibrium
It's to specify.
solution of this is Fi0, and that Fi0 is whatever I pick.
Right.
If I can pick anything I want,
No, Fi0 has to be a Maxwellian with the right density moment.
but a Maxwellian is whatever I call it. It doesn't. It's no. There's no. It doesn't have to be the same. It doesn't have to be an e to the minus something squared. It can be anything I want. All I need is that it satisfies these conditions when I turn the integrals into sums. But I can pick. But that still leaves me quite a lot of choice about what function I use.
I'd be surprised if you get the right jump conditions and viscous heating and shock.
Yeah. All you need is the right is enough correct moments.
But this isn't the real distribution of anything. It's just the invisible.
So when I'm deriving
logical thing,
when
right?
I'm
It doesn't
deriving
Invisible
Navier,
hand of Paul.
It's the invisible hand of Paul.
when I'm deriving Navier-Stokes, all I need is the moments. And the nice thing about this thing is you multiply it by any power of xi, and you integrate and get some polynomial in U. I can just.
But this collision operator also has important properties that it relaxes to a state of maximum entropy. That's how it generates heating.
But he doesn't care about any of this, right? Because he's constructed that invisible kinetic theory just to help him solve the fluid equation.
So I can
It doesn't have to be a real kinetic theory of anything.
I can construct the real kinetic theory, the fake kinetic theory, so I get the right viscous heating and the right heat conduction and everything in the energy equation at Navier-Stokes Fourier order exactly the same as in real kinetic theory.
I guess another way of expressing my confusion, this is a multiple time scale expansion in tau.
Yeah.
And you got this nice formula at first order, but you get something else if you worked it out the second order.
Yes, I would, but
And of course that's supposed to be small.
Yeah.
But then isn't there? But then if you were to look at, say, high order structure functions, you're asking about, weird effects, and maybe there's a maximum one you're allowed to compute unless you worked out the.
but my structure functions are just defined in terms of Navier-Stokes quantities. They just involve the fluid velocity.
Suppose you work this out the second order. Wouldn't you have a different stress tensor?
Well, I'd have an order Tor squared correction.
Yeah.
Yes.
So it wouldn't be precisely Navier-Stokes then.
No, but I could, for instance, if I'm trying to do incompressible Navier-Stokes, I can dial down my Mach number, and that has the effect of dialing down Tor, because at Tor is.
I know there's a small correction.
But I can make that small correction as small as I please. So I can converge to Navier-Stokes.
I understand it converges
Yeah.
to Navier-Stokes, but for any finite tau, it's not precisely Navier.
No, and similarly for any finite grid, it's not precisely Navier-Stokes because I got a spatial truncation
Well,
error.
right. I'm just trying to understand conceptually.
We had a fellow in our community who went around about 12 or 13 years ago named Kim Mulvig, who told us that this was exact to all orders. And he really sold it very, very hard. So we're still reeling from this.
Well, so it's interesting in the sense that there's nothing you can really point to and say this is the spatial truncation error. But so a lot of numerical conversion studies have verified that you get second order convergence. So can I go on to talk about MHD? Okay, so I don't need to tell you. I don't need to tell you anything about MHD except I'm setting out to do non-relativistic pre-Maxwell's equations, so I'm just trying to solve this set, and the electric field is now just a name for the flux that goes into the induction equation. It doesn't have any independent existence. It's lost its time derivative. It's convenient for me to try and make this look more like a momentum equation, so I'm going to write its divergence of something lambda, which is an antisymmetric tensor I build out of E just by taking the epsilon that goes in the cross product, if you like, into this lambda. Just notation. And then I need to get MHD, I need some form of Ohm's law, and I'm just going to focus to start with on resistive MHD. I plug that in there. This is the system I'm going to try and solve. So the differences from regular hydrodynamics are I've got a Lorentz force in a momentum equation, and I've got an induction equation. Lorentz force is easy because I can rewrite it as the divergence of a Maxwell stress, and then my implicit momentum equation is again in conservation form with a Maxwell stress in here. So I just change my equilibrium momentum flux to put in the magnetic pressure and the magnetic tension, and then there are formulae which tell me how to go from the moments to the distribution functions. I've just thrown away the n and the j, which I can do for isothermal fluid. So this is a formula for the distribution functions, given I want this momentum flux at the Euler equations. And then I can plug that in, do the Chapman-Enskog expansion, and I get Navier-Stokes out with a Lorentz force. Notice that I only need B at lattice points, and in the induction equation I'll only need U at lattice points. So the two bits, the hydrodynamic bit and the magnetic bit, are only coupled through the macroscopic variables, which makes it nice and modular. You can take your favourite Lattice Boltzmann hydrodynamics code and then bolt on an extra bit to do MHD. The induction equation is the tricky one, because if I take a Boltzmann equation that looks like this and take its first moment, multiply by xi and the sum, what I get is a momentum equation. And this thing pi, the momentum flux, is by construction a symmetric tensor. Now this is good in hydrodynamics because it means the scheme's got angular momentum conservation built in. But it's a pain trying to do a magnetic field, because what I want is to have the analogue of this tensor being antisymmetric. But I can't do that because this is forced to be symmetric. So there's a problem trying to evolve the magnetic field. What was done originally, this is late 80s, early 90s, was to set up with you had two distribution functions with two indices and two sets of velocities, one for the magnetic field and one for the fluid velocity. So you defined the moment to be, sorry, the momentum to be the moment with respect to one set of particle velocities, and the magnetic field to be the moment with respect to the other set of particle velocities. And then the lambda tensor was a moment with respect to one of each, and that broke the symmetry problem. And there's been some recent work extending this into 3D using 3 sets of particle velocities, so you have a third set for the electric field. And there's also some early work in 2D where you just use a flux function, and they're using effectively the n moment in the Lattice Boltzmann hydrodynamics to carry around the flux function and using finite differences to get the field and the currents. So,
I don't quite understand these top equations.
So I'm going to, whereas before I had an f which just had a 1 suffix and I, and I took some moments with respect to the xi. Now I'm going to have, or not me, but these people decided they wanted to have 2 sets of velocities with 2 indices, an a and a sigma, and these are a set of constants, and these BA sigmas are another set of constants. So my moments are now defined as double sums with a distribution function with 2 indices and a particle velocity with 2 indices. But this, well, one of the reasons having it all tangled up together is you then didn't have independent control over the Reynolds number and the magnetic Reynolds number, or equivalently the viscosity and the resistivity. So I came up with this approach of trying to decouple things. So I write down a Boltzmann BGK-like equation for the magnetic distribution functions, and the twist is to make these things vectors. So you think about having populations of little bar magnets, rather than just point particles or spheres as in the Boltzmann equation for hydrodynamics, so they can carry a magnetic field as little vectors. I define my macroscopic field to be the sum of these vectors G, and the equilibrium is going to also be equal to B. So when I sum up this equation over all the particle velocities, I get my induction equation. This condition ensures the right-hand side vanishes when I sum, and this is my electric field tensor. So now I've avoided the symmetry problem because this is one index on a xi, another index on a g, so there's no reason this has to be symmetric. And then my lambda, I can take another moment, I get the evolution equation for lambda, collision term relaxing it to equilibrium, divergence of another moment I call m, which has got two xi's and a g. So I want to get a resistive MHD induction equation out of this, and I do it by multiple scales, just the way I get Navier-Stokes out of a real Boltzmann equation. So I have multiple scales expansion of G and time derivative in powers of the magnetic collision time tau B, solvability condition, which says that these higher terms don't contribute to the macroscopic magnetic field, just as in hydrodynamics you would say that the higher terms in the expansion of F don't contribute to the density and the momentum. Equivalently, I expand the lambda and the m tensors as series in collision time, but I leave B unexpanded. I'm going to choose my lambda 0 to be UB minus BU, and I stuff that in at leading order. I get ideal MHD. So here are some equilibria which have the right moments. The 0th moment is B, first moment is lambda 0. And now I need to get the first correction to lambda 0 in order to get the resistive term. And that's given by the leading order evolution equation for lambda, the same pattern as before. Leading order time derivative of leading order value, divergence of leading order flux is the first correction. For this expression I can work out m, it's something to do with b as a delta, and this thing theta is just a constant which depends on the velocity lattice, and it's usually 1/3. And I've worked out my lambda 1. That's something to do with the gradients of b, and there's a small order Mach number cube correction. I'm scaling here assuming the alphane speed and the fluid speed are comparable. So I plug that in and I'm solving resistive MHD in this form with a resistivity proportional to the magnetic collision time. And what's also interesting to note is I can get at the current from the non-equilibrium part of the distribution function. So I can get the current at grid points without having to do any differentiation. I just work out from my distribution functions what the lambda 1 is, which I approximate as lambda minus lambda equilibrium, put an epsilon in front, and that gives me the current. And then I discretize, discretize this by integrating along characteristics the same way I discretize the hydrodynamic Boltzmann equation, so I get an MHD scheme. Now you might worry that I'm going to need an absurd number of degrees of freedom. Now I'm going to have to carry around vectors. But if I do a count, it's not so bad. I don't need the third moment of the G's, as I need the third moments of the F's to get the Navier-Stokes viscous stress, so I can get away with fewer velocities for the magnetic distribution function. So in 2D, it's typical to use 9 for the hydrodynamics, but I only need 5, or really you could get away with 4, but 5 isn't much more stable. So I just keep the particles going along the axes as shown by the thick lines. And in 3D, you might use 15 or 19 for the hydrodynamic part, but you only need 3 copies of the second velocity lattice for the magnetic distribution functions. So you do a count up, you get 9 degrees of freedom for the fluid and 10 for the magnetic field, or 15 for the fluid and 21 for the magnetic field. So it's roughly comparable. So this is from a paper where I introduced this, just a Ilzag-Tang vortex benchmark, and I showed second order convergence to all spectral solutions. And this is the Mariani and Strauss magnetic island doubly periodic coalescence problem. This is evolution of flux function. I start with a square periodic array of islands, and I give them a little nudge so that they merge pairwise. And what's interesting here is I'm plotting my peak current versus time, and these wiggles are resolved sound waves because I'm doing a compressible scheme with a finite Mach number. They were doing Godunov plus projection onto incompressible flows. And if you look at the case of high magnetic external number, small resistivity, they look pretty much the same. But if you go down to the more resistive case, they look quite different. And in fact, having checked both theory and spectral code, this one is right and this one is wrong. The reason this one is wrong is because they were just doing time step controlled by the advection CFL condition. They weren't having a time step that's short enough to get the diffusion right. As I said, so I got a spectral code which agrees with this, and also you can just look at the decay of the in linear theory before the instability kicks in, and this is perfect. So those are some like 2D ones. Now, more recently, there's a group in Santa Barbara who are trying to turn this into a gadget for, or software package for designing cooling systems for nuclear reactors. So how you pump liquid metal around magnetic fields. And this is one of their pictures showing they're trying to simulate 3D Hartmann flow using the 3D version of this algorithm. And there's another one by George Verhallo and co. where they've run a 1800 cubed MHD turbulence simulation and produced lots of spectra and pretty pictures. And Alex, you still think this is the biggest one you've heard of?
MHD.
MHD, yeah.
Yes.
So this seems to be the biggest MHD turbulence simulation that's been done.
Biggest conventional one I know about is it's a funny number. It's 1,583 cubed. I don't know. There's something special about the number.
I've heard that number coming up
You
before,
probably know
yeah.
about this. That was done at NCAR, and that was a hero simulation, which they could only run for about a millisecond.
But resolution-wise, that was a spectral.
It was a spectral simulation, yes. There was Menini. Well, actually, I don't know if Menini is good as spectral. Probably. So this is probably comparable, is the point you're trying to make, right?
I'm not going to criticize.
This is still pretty good, even.
Well, it's just that you throw more horsepower up and it scales beautifully. You just feed it more CPU and it will scale out to bigger grids. So that's all the old stuff. Now, how much time do you want to go on? Or stop?
People can wander off.
People right.
At some
So,
point, people will just start.
okay, so I'll now start talking about more recent stuff. So this is going back to what I was saying, all that stuff about N's and J's. So the point is that you can get the stability improved if you set those N's and J's just to equilibrium every time step and forget about them. So collision operator becomes a case of relaxing the momentum flux of pi thing towards equilibrium, then reconstructing the distribution functions. There are no post-collisional twiddles marking out rho and u because they're conserved by collisions. Then I do the streaming of the post-collisional distribution function. And the magnetic field only changes this existing setup for doing matrix collision operators for hydrodynamics. You just change the expression for the pi zero. And some of the more recent MHD work has used this. It gives you better stability. Sorry, I lost the slide. Oh, never mind. So I was going to show that if you look at those peak current versus time thing, as you can run stably at very coarse resolutions, but it's not actually very accurate. And as you increase the resolution, you converge to the more accurate current profile. I can use the same technology to do Baginski MHD. And thanks to Alex for suggesting I did this. So this is looking at a strongly magnetized plasma. So I'm not going to keep the Navier-Stokes viscous stress. I'm going to try and do something appropriate to a plasma where the particles are doing spiraling around field lines. So the point there is that this particle can collide more easily with this one on the same field line than it can with this one, which is closer, but on a different field line. So the effective mean free path in this direction is the gyro radius, not the mean free path you'd have in an unmagnetized plasma. So that gives you a viscous stress that's approximately lined up along the field lines, as Baginski derived from kinetic theory. But if you try and run with that, you find that it's unstable. Also, if you try and do a channel flow problem, you can't sort out the boundary conditions at the wall. So I'm going to regularize with a small bit of isotropic viscosity. I'm going to call mu perpendicular, which is much smaller than mu parallel. So if I think about having some horrible tensor relating the stress to the strain rate, choose axes lined up with B, the first coefficient is mu parallel, everything else is mu perpendicular. This has been met, or something similar has been met in Lattice Boltzmann circles for liquid crystals, but in liquid crystals, these two things are roughly comparable, maybe a factor of 3 or 4 different, whereas in a strongly magnetized plasma. This is very small compared to that. And this is easy to implement because when you're doing the collisions of the momentum flux, you pick out the part that's lined up with the magnetic field and you collide that with a different collision time to the rest of it. So I've got my usual formula for the equilibrium, my collision, this, here I apply uniform relaxation time torque perpendicular to the whole of the momentum flux, and I pick out the components along the field line and change this from torque perpendicular to torque parallel. And these are just related to the parallel and perpendicular viscosities, then I reconstruct and stream. So it's a small change to the algorithm and it's a small change to the code. So here's a code fragment. If I work out my pi0 in terms of density, velocity, magnetic fields, I work out the component along the direction of b hat, the unit vector of the magnetic field. I work out the equilibrium component, collide those, collide the rest, then reconstruct the distribution functions. So it's a small change to the code to make it do Baginski MHD. I got a few preliminary benchmarks doing Hartmann flow. So the usual stuff, magnetic field across the channel. I scale it like this, so my unit vector is like that. Viscosity ratio I'm going to call epsilon squared. So this is running the Lattice Boltzmann code till it reaches a steady state, compared with solving the ODEs that give you a steady profile. Those are the green lines. Lattice Boltzmann computations are the dots, so this is the isotropic case. This is, let's see, viscosity ratio would be epsilon squared, that's 10 to the minus 4. And it agrees very nicely. And similarly with the velocity, the highly accurate and trustworthy solutions of the steady state ODEs are these black lines. Lattice Boltzmann are the thicker coloured lines, and it agrees very nicely. And it converges, at least so far. So this is quite a technical chunk of stuff on trying to do current-dependent resistivity, which is possibly...
Ask you a quick question.
Sure.
What ranges of beta, magnetic and thermal pressure ratios, can you do? I had a little trouble with that.
Well, I'm always doing the wrong way round to what you would want.
You're doing high beta.
Yes.
Yeah. So a couple of weeks ago, we had people here who were doing high beta Baginski simulations of accretion flows, and they might be very interested in this kind of technology, I would imagine. For fusion systems, we're often at the wrong, the low beta end.
And also Baginski's not going to work because the mean free path's too big.
Oh, that never stops anybody.
So I've done some 2D Baginski simulations, but at the moment I'm still rewriting my spectral code, so I've got something to compare against. Otherwise I'd be just showing pretty pictures that I can't vouch for. But I'll do current-dependent resistivity, which people in the sort of the space weather community like. So I make my resistivity be a function of the current density. And a lot of work's been done in Lattice Boltzmann circles on so-called generalized Newtonian fluids where you make the viscosity depend on the strain rate. And the attraction there is you can get the strain rate like the current out of the non-equilibrium distribution function, so you don't need to do any differentiating. So this was quite easy to implement in Lattice Boltzmann hydrodynamics. But the problem with the MHD case is what I'm showing you I'm simulating is this, whereas what I should be simulating is that with a curl instead of a div grad. And then the problem is that as soon as eta starts spatially varying, I get spurious grad eta terms from here, which aren't in there. And there's always a problem with div b, but it vanishes when div b 0. And I should have said that this algorithm maintains div b down at round-off error quite happily.
Yeah, but this is, I mean, once you make eta dependent on j, that's already a fudge, right? So is this a bit of an overkill to do it properly?
I don't think so, because Maxwell's equation says this should evolve through a curl.
That's true.
There are physical models and get eta dependent on theta.
In that way.
Well, J over CS. And I
Yeah.
But that's fixable because with a more complicated collision operator. Before I wrote down this and then derived moment equations from it. So instead, what I want to do is write down the moment system I want and then reverse engineer the collision operator. And the way to do that is to figure out a basis of moments, just as I did before for the hydrodynamic side. This is a bit. Start just doing the scalar case where I've got the lattice with just keeping the 5 velocities. So I've got 5 moments, density, if you like, 2 components of momentum, and then just 2 components of stress, which is all I can fit with 5 velocities. And then I can work out a relation between the moments and the distribution functions with a full rank 5 by 5 matrix. So I can invert that matrix to go back from the moments to the distribution functions. There's quite a nice formula for the Fs if I treat the equilibrium as a special case, and the same thing works in 3D. You just have to plug in a pi zz over here. So my moment basis for the magnetic distribution function, so I got 2 components of B, that's 2 degrees of freedom, 4 components of this lambda thing, I'll come back to why they're 4 later, that's another 4. And if I look at the M tensor, 4 of these vanish identically because this product, psi alpha, psi gamma, is 0 when alpha and gamma are different. So these are the only, these are the 4 that are not identically 0, so that's my remaining 4 degrees of freedom, and I've got my 10, 2 plus 4 plus 4, which gives me my basis. So I can now specify the collision operator by what it does to B, lambda, and M. And I can get an evolution equation for M involving the 4th rank tensor, but again, I've got a lot of the components are identically 0, so in fact I can write it just in terms of my lambda. So I get an evolution equation for M coupled back to lambda, just as the evolution for equation for lambda involved M. And this all works pretty much the same in 3D. It's just more to write out. So now what I'm going to do is work out what collision operator I want by specifying its action on these moments, and then I can reconstruct the distribution function. This is just like doing a Gross-Jackson collision operator in continuum kinetic theory. You specify what you want for so many moments, and then in continuum kinetic theory, you just use a BGK approximation for the rest. In discrete kinetic theory, I can just specify everything. But I also need to chop up my lambda, because I tried to tell you that the lambda was something that's anti-symmetric and related to E like that. Because this made my induction equation look like the kind of thing I knew how to solve. So in 2D, I should have something that looks like this. And that's correct at equilibrium, but if I go past equilibrium, I find that the correction is not anti-symmetric, and I can't juggle things to make it anti-symmetric, because then it also has to be symmetric on other indices, and then you find you can't satisfy everything. So I need to decompose lambda into an anti-symmetric part, which is the real electric field. There's an isotropic bit, which has got something to do with div B, and that's the thing that's maintained at round-off error, and there's an extra bit, which is symmetric and traceless. And that's where the grad div eta comes from. So if I want to change the resistivity and make it spatially varying, what I do is I collide the anti-symmetric part of the electric field. Anti-symmetric part of lambda, i.e. the electric fields, with a spatially varying collision time, and the 2 just comes from when you split into symmetric and anti-symmetric parts and recombine. And the symmetric part of the constant collision time, and then reconstruct. So I've got a collision operator that applies a different collision time to the anti-symmetric and the symmetric parts of the lambda tensor. And I also want my resistivity to depend on the current, and I've got the current from the curl of B, or the epsilon times the non-equilibrium part of this lambda tensor. So in vector notation, here's an expression for my current in terms of the non-equilibrium electric field, which has got this lambda down here. So I bring all this up here, noting that lambda depends on J, and I get an equation for J, which I solve by Newton's method, typically just needs 3 or 4 iterations. And I can find lambda, and I can collide, and then I can reconstruct. So I'm solving my induction equation in this form. The varying bit is correctly in the curl-curl form. This comes from the fact that I need to have an invertible collision operator, so I can't kill off the symmetric part completely, but I can keep some small background resistivity and then have this, the spatially varying part, correctly in the curl-curl. And again, doing a Hartmann flow problem, I can compare for the kind of models people use. So we've got background resistivity 1 plus current over some threshold to a power. This is comparing current, reference, independent solution for steady state ODEs, dots, lattice Boltzmann computations. It's all working very nicely. Also, Tang vortex with current dependent resistivity, as you'd expect, you get a fatter and less intense current layer when you make the resistivity go up where the current's big. And I can check convergence to spectral that I'm getting roughly second order convergence towards spectral for this problem. So you're doing the current dependent resistivity with spectral code is fairly miserable because you have to do very short time stepping to capture the diffusion. For my constant resistivity code, I take all that out of an integrating factor, so I can do the resistive decay of Fourier modes exactly. And then if you don't do the fiddling around with treating the anti-symmetric part separately, you get this. This is what's this reconnection of magnetic islands again? So this is the vorticity, and you get this funny-looking pattern around the current layers when you have that grad eta term. When you do it properly, you get a more usual-looking quadrupole structure around the current layers. I just want to finish off with a few minutes on Maxwell's equations. So if I start with my full evolution equation for lambda, which I got from taking moments of my magnetic Boltzmann equation, my electric field, which is going to be the antisymmetric part of lambda, evolves according to this. And I can choose my collision operator to apply a collision time to m that's much shorter than the collision time for E, and seek solutions where on a time comparable to tau E, which is much bigger than tau m. So now I leave B and lambda unexpanded, so lambda's become a slow variable too. I just expand m. And at leading order, I've got m equilibrium is this thing again with the delta and B. So I plug that in, and to sufficient accuracy, I get this, my evolution equation for E, or leading order in my Chapman-Enskog expansion. And this, I untangle this, and I just get something involving curl B, and a speed of light, which is to do with the lattice speed, and some square roots and things. And my equilibrium E0 minus U cross B, so what I've got is this equation. This is the evolution of the electric field under my lattice Boltzmann MHD scheme.
How do you handle the corner velocities are square rooted 2 faster than the side velocities? So how's the speed of light handled there?
The speed of light is an average property. It's not a. It comes. So this thing theta comes from the sum. So I can form this tensor out of the, and that's theta. So it's not a property of the individual lattice velocities. It's a property of the weighted sum.
So the individual particle velocities are superluminal?
Yeah. Well, you have to have that because you can't have anything propagating faster than the particle speeds. So that equation, I've got full Maxwell equation for E has come out in conjunction with Ohm's law, and this is all conductivity that's to do with the collision time, an effective mu naught, and an effective C. So while I've set out only to do MHD, I've actually got a full set of Maxwell's equations because the kinetic model always has to give me a first order hyperbolic system with collision terms, and Maxwell's equations fit that, whereas the resistive MHD induction equation doesn't. And to make that a bit more systematic, what I did before was to expand lambda and m in a small parameter, assuming they were both rapidly evolving, and B alone was slowly varying, and then that gave me my correction for lambda. Or in Van Kampen's terms, I took B to be slow and lambda and m both fast. To get Maxwell's equations, I take m fast, but now I take B and lambda to be slow, and that changes the expansion. And then this gives me Maxwell's equations. Just by plugging the expansion for m into the exact evolution equation for lambda. And test that by putting in a current distribution, looks like this, so it's a Gaussian made antisymmetric, switches on at t equals 0 and then oscillates. And the reason for choosing this particular form is it's then easy to get a spectral solution of Maxwell's equations. Because you can just write ODEs for these and the solution in terms of this ODE. So I got the movies. So this is radiation of electric field along the current which is going into the board, and a component of magnetic field as computed using this scheme. And of course the charge conservation looks after itself. Oops. And then so I'm getting second order convergence under grid refinement towards spectral solutions of the same problem. So to conclude, the attraction of this Lattice Boltzmann approach is you get linear constant coefficient advection, so it's very easy to discretize and implement on a computer. All the nonlinearity happens locally at grid points in the collisions. So my colleague Saro Suchi likes to say nonlinearity is local, non-locality is linear, where non-local just means next grid point. And we keep just enough kinetic theory to recover a Navier-Stokes level approximation, and at the moment not more than that. The MHD approach I should use is a vector distribution function to carry the electromagnetic fields. This gives you a parallel algorithm which George Valhalla's group have shown, run it on the blue gene as well as on the Altics, and you can scale up to 32,000 processors and get linear scaling. The electric field also though has a symmetric part, and you need to worry about that if you want to use matrix collision operators to do other kinds of plasma equations, for instance doing the current dependent resistivity. And then finally, although I only set out to do non-relativistic MHD, in fact I found that the scheme has the full set of Maxwell's equations in. In some sense, it's saying that the physics works like this. It's about first order hyperbolic systems. And when we get parabolic things out, that's an approximation. So this is, I think, actually quite a good model for what's really happening. And with that, I'll stop. Thank you.